Hello everyone and welcome back to another video. In this third episode of my number theory series, I wanted to go over the concept of greatest common divisors and prove a few useful theorems that we're going to use all throughout our number theory journey. In the textbook, this particular section is called greatest common divisors and linear Diophantine equations. I decided to split the section into two different videos because this is a longer section. I think covering the entire thing would take multiple hours, and I want to make my videos a little more concise so as to not post these multi-hour lecture videos that nobody in their right mind would even want to watch. Like, that's longer than a college lecture, and people struggle to attend those. So, but with that aside, let's actually get into the concept of the greatest common divisor. And we're just going to start with some definitions. So let me start writing, and apologize in advance for the handwriting. I don't practice writing on these things very often. But for the first definition, we're just going to talk about what a common divisor is. So a common divisor of two integers A and B. See, there's like a slight delay when writing with this thing. Is an integer D such that D divides A and D divides B. So this is pretty simple. It's just like a factor of both of these, and it's a common divisor, divides both A and B. And two facts about these are every two integers has a common divisor of 1, regardless. 12, 1 divides 12, because 1 times 12 equals 12. 1 divides 3,625,734, because 1 times that number, I guess I'll write it now, equals that. 1 is a divisor of every two integers, because 1 divides every two integers. So 1 is a common divisor of these two. And then also the number of common divisors on any pair of numbers is finite. Because of this, one of these divisors is going to be larger than all the other divisors, which is where we get this concept of the greatest common divisor that we're going to discuss. So let's look at another example. Let's look at 8 and 12. Well, 8 has the following factors: 1, 2, 4, and 8. And 12 has the following factors: 1, 2, 3, 4, 6, 12. So which of these are common divisors? Well, obviously 1. That's considered like a trivial common factor. 2, they're both even. Not 3, because 3 only divides 12. 4, yes. Not 6, not 8, and not 12. So the common divisors of 8 and 12 are 1, 2, and 4. And that means that the greatest common divisor is 4. But let's give a definition of the greatest common divisor, because that's a very important concept. Oh no, what does this button do? Oh no, I started at the bottom of the page. That's funny. Okay, let me, I wonder if I can just like select it and move it. Never actually done this before. Yeah, let's do that. That's good. I was resizing the page before starting this, so it makes sense that it's like in the complete wrong area. Technical difficulties. Okay, now that we have this, this definition of a common divisor, let's get into what the greatest common divisor is, because that's going to be the topic of this video. So the definition, and I need to switch back to the pen. So the definition of the greatest common divisor is this. The greatest common divisor or the GCD of two integers A and B not both 0. Because if they're both 0, like every single number divides 0, because any number times 0 is 0. So the GCD would be undefined. Not both 0 is the largest integer D such that D divides A and D divides B. And this is denoted it's denoted the GCD of A and B, or in number theory we'll just use this ordered pair, because now this is used in real analysis for like an ordered pair on a graph, but this is completely different. When you see this in number theory, this refers to the GCD. We use the GCD far more often, and it's a very, very, very common concept all throughout number theory. So we just use this ordered pair notation quite a bit of the time, and I'm going to interchange between both of these so you kind of get used to that notation. And another way of saying this is that D is the greatest common divisor of A and B if the following conditions hold. D divides A and D divides B, and then C divides A and C divides B implies that C is less than or equal to D. So these two formulations are things that we're going to use quite a bit. This is how we're going to show, like, if something is a GCD, we have to prove it divides A and B, and then we have to prove that for any other divisor of both A and B, or any other common divisor, C is less than or equal to D. So that's the basic concept of greatest common divisor. And then another concept that's going to be very important when we're looking at GCDs is the concept of relatively prime. So the basic definition here is if GCD A and B equals 1, then A and B are relatively prime. So for a few examples of this, or just to check if numbers are relatively prime, Basically what this means is it has no non-trivial common divisors. There's no other numbers that divide it. Yeah, so I think, and these numbers also play a very special role all throughout number theory. They're very like dissimilar numbers. They don't have any common divisors. So it's like two pairs of even numbers. They're both divisible by 2. This doesn't even have that. They're very different numbers. So let's look at some examples. So the GCD of 36 and 22 does not equal 1 because both numbers are even. So these are not relatively prime. 36 and 22, their GCD is greater than or equal to 2. Another example, look at like 45 and negative 15, because and that GCD is also not equal to 1 because both numbers are divisible by 5, so the GCD is greater than or equal to 5. And then along with that, let's look at an example where they are actually relatively prime, so like 15 and 28. That equals 1 because if you look at the factors of 15, or the divisors of 15, you have 1, 3, 5, 15, and if you look at the factors of 28, they are 1, 4, 7, 28. So what you'll see is the only common divisor is 1, so there's no non-trivial common divisors. So the GCD of 15 and 28 is 1, which means that these numbers are relatively prime. Okay, so with this, let's look at a few basic theorems regarding GCDs. And these next two theorems that we're going to look at are going to use the division algorithm, and they're going to be useful in later proofs, and then also in defining an algorithm to figure out what the GCD of any two integers is. And this first theorem that we're going to look at is a bit simpler than the second theorem, but it's going to be helpful in understanding that second theorem. So, theorem 1.32, and then start, let A and B, R and K be integers if A equals NB plus R and K divides A and K divides R, then and K divides B, sorry, then K divides R. So basically this is looking at the division algorithm, and it's saying if this other number K divides both A and B, it also divides the remainder of A and B. So let's look at the proof. So we're just going to start by defining all these terms, all these letters, N, B, R, K, all be integers, where A equals N, B plus R, k divides A and k divides B. And then by the definition of divisibility, which we learned about before, then A divides, or A equals kx and B equals ky for some xy, or some integers x and y. So what this means, we can write out this original equation, A equals nb plus r. So that means that kx equals nky plus r. And what that means is if we subtract from both sides, kx minus nky equals r. So then k times x minus ny equals r. So now what we have is r written as k times some integer, and because of this, thus k divides r. So we have our proof. And then this next proof will be longer. Let's see, I think I have enough room. We'll see though. So what theorem 1.32 shows us is that if you have these integers, or if you have this division algorithm breakout for A and B, where the quotient is n and the remainder is r, and you have k divides A and k divides B, then k divides the remainder that you get when you use the division algorithm on A and B. So that's what theorem 1.32 shows us. So let's use this to show a useful theorem in understanding how to derive the greatest common denominator between any two integers. So let A be n1 and r1 be integers with A and B not both 0. So we'll say if, and the theorem is if A equals n1b plus r1, then the GCD of A and B, the two numbers that we're using the division algorithm on, equals the GCD of B and the remainder. So here what we have, so here you can already see how this is kind of going to be useful, because you know if it divides both A and B, it also divides both B and R1. So let's look at these results. Or let's look at this proof. So we're going to start by just defining all our numbers. So we're going to let A, B, N1, and R1 all be integers with A and B not both 0, and let A equal N1 B plus R1. And then to start, we're going to note that since A and B are not both 0, the GCD of A and B is well defined. Additionally, we'll note that because the definition requires both integers in the GCD to not be 0, so A and B are fine. But the question is, are B and R1 fine? Like, is the GCD between those two well defined? Because if they're both 0, then it's undefined. And it's possible that B is 0 because all it says is both A and B are not 0. So if B is 0, A is not 0, but then what does that say about R1? Well, we're going to note here that B and R1 cannot both be 0 because of this formula right here. If B and R1 are both 0, that means that A is also 0, so both A and B would be 0, which violates this definition. So because A and B are not both 0, R1 also cannot be 0. So we're just going to write that out quick. Note that B and R1 are not both 0, since this implies that A equals n times 0 plus 0 equals 0, which violate the condition that are not both 0. Okay, so A and B aren't both 0, so this means that B and R1 are not both 0, which means that this greatest common divisor is well defined. So it is actually a number that we can calculate. Okay, so another thing to note is basically that if we can prove that for any integer that divides both A and B, that integer also divides both B and R, and that the converse is true. So basically, I'll write this out before I explain it. So if we can prove this statement true, that if C divides both A and B, that means that C divides both B and R1, and if C divides B and R1, it also means that C divides both A and B. Then we have shown that AB equals BR1. So why is this? Why is this sufficient to prove this? The reason why is because if you can prove this former statement, this biconditional statement, that means that A and B have the same list of divisors as B and R1. And since they have the same list of the divisors, because if it's in the list of common divisors for A and B, it's also in the list of B and R1, and the reverse is true, that if it's in the list of divisors for B and R1, it also means it's in the list of divisors for A and B, or common divisors for A and B. That means they have the same list of common divisors. Those lists are identical. That means that the greatest common divisor is also the exact same between A and B and between B and R1. So that means that those GCDs are in fact equal. So using this statement, since this statement is identical to this statement, we can proving this statement proves that this statement is true. So to prove that these GCDs are equal, we're going to prove this statement. So let's start by proving the first direction. And here we're just going to let c be an integer such that c divides a and c divides b, so a equals ck and b equals cl for some k and l that are integers. Okay, so we have that. So a equals n1 b plus r1. So we have that from before, that a equals n1 b plus r1 implies by the previous theorem that we proved, 1.32, that c divides b and c divides r1. So by citing that theorem that we previously proved, if you remember it, if a can be written as nb plus r, then if k divides a and k divides b, then k divides r. We've basically shown that here because we know that k divides a and k divides b right there. So it also means that, c divides r1, and we already know that it divides b. So that's that first direction. Let's prove the other direction. Let c be an integer such that c divides b and c divides r1, so b equals cp, b equals cq for some pq in the set of all integers. So what we have here is that a equals n1 b plus r, and this means that a equals n1 cp plus cq, which means that a equals c times n1p plus q. Hence, c divides a, which means c divides a and c divides b. Okay, so we've proven the other direction now, that if it divides b and the remainder of a and b, then it also divides a and b. And because of this, we have proven what we set out to prove. Thus, c divides a and c divides b, if and only if c divides b and c divides r1. So the GCD of a and b equals the GCD of b and r1, which is what we were trying to prove to set out from the start. Okay, now what does this actually get us? Well, using this theorem, we can come up with an algorithm that gives us the GCD between any two integers. And this algorithm is called the Euclidean algorithm, named after the old Greek mathematician Euclid. And we will go through how it works up next. And I'll make sure to actually change the title this time, the thing at the top. Okay, so the Euclidean algorithm is based on this last theorem that we just proved. And it gives us a basic algorithm to find the GCD for any two integers. And it works by repeatedly using the division algorithm on two integers and then applying that theorem 1.33. So basically, to find the GCD of A and B, so we're concerned with GCD of A and B, and we're gonna assume in this case that A is greater than or equal to B, which is greater than or equal to 0. And if this isn't true, you can just switch the order of A and B. So like say you have 152 here and 3 here, just switch the order, then make A 152 and B 3. That works as a sort of without loss of generality thing. But not both 0. So what we're going to do, using this, we're going to start by just writing A equals B N1 plus R1, where 0 less than or equal to R1 is less than B, which is possible by the division algorithm. If you remember the division algorithm from the last video. And what this means is that GCD from theorem 1.33, so this is division algorithm. And then this is theorem 1.33. This means that GCD A B equals GCD B R1. Okay, so what does that mean? Well, now we have B and R1, whose GCD we're going to try and find. So let's just apply the division algorithm again. And this means that the GCD of B and R1 equals the GCD of R1 and R2 by that theorem we just proved. Now from here, what do we get? Well, from here, we can continue doing this process, and eventually we will reach this chain of equalities basically we want to continue doing this until the remainder is just equal to 0, until the remainder of the previous one literally just divides B, until the remainder is equal to 0. So then up next we're going to have B R1 and then GCD R1 R2 and then the GCD of R, we'll say Rn minus 1 and Rn. We'll say Rn is the one that's equal to 0. So since this is just equal to 0, 0 divides all numbers, so sorry, that's not true. A divisor of 0, every single number is a divisor of 0, so Rn minus 1 would be a divisor of 0, and it's also a divisor of Rn minus 1. So Rn minus 1. So the GCD of A and B ends up being this Rn minus 1 number here. So this is the very abstract basic formulation of how this works, but to understand it, you're going to have to go through a few examples. And the nice thing about this is you can do this with any two integers. So if you're just sitting at home right now and have some extra time, you can practice this by literally just coming up with numbers. Coming up with examples for this type of problem is incredibly easy because literally you just have to think of two random numbers and then go and do the algorithm. So for the first example, we're going to look at the example the book provides, which is GCD of 51 and 15. And then I'm just going to write out the actual division algorithm. If you want to calculate this on your own, you're going to have to go through the long division process. So that's what you'd have to do if you want to do this. But for me, I'm just going to write down this stuff because I already did this long division earlier. And just to save time, because we're already at 35 minutes and there's still a decent amount more to cover in this video. So by the division algorithm, 51 is 15 times 3 plus 6. So it's 45 plus 6. Which means that 15 equals the GCD of 15 and 6. So then what we can do is break up 15 and 6. So if 15 equals 6 times 2 plus 3, which means that 6 is 6, 3. So from there, we can apply the division algorithm again, and we get 6 is 3 times 2 plus 0. So the GCD of 6 and 3 is equal to the GCD of 3 and 0, which is just equal to 3. So now what we have is the GCD of 51 and 15 is just equal to 3. Okay, so that's one example. And let's look at some more like special cases where the division algorithm doesn't work. GCD of 2, 56 and 0. We can't actually apply the division algorithm here because no matter what you multiply 0 by, you're never going to get anywhere close to 256. But the GCD of any number and 0 is just the absolute value of that number, so that's just 256. You're already done. You don't have to apply the division algorithm at all. So for the third one, we'll look at the GCD of 1,001. And for this, it's only one step. 1,000 equals 1 times 1,000 plus 0. So GCD 1,001 equals GCD of 1 and 0, which is just equal to 1. And the GCD of any number in 1 is just going to always equal 1. So the GCD of any number in 0 is equal to that first number. The GCD of any number in 1 is always going to equal 1. That's a weird looking 0. Okay. So for the fourth one, we're going to do one more example, which is going to be a more involved example here. So the GCD of 162 and 31. So to start, we're just going to break apart 162 by using the division algorithm on it and 31. So 162 is 31 times 5 plus 7. So GCD of that is GCD of 31 and 7. And then now we can split apart 31 and 7. So 31 is 7 times 4 plus 3. So next we'll have 7, 3 in this chain of equalities. And the next 7 is 3 times 2 plus 1. So we'll add 3, 1 to the chain of equalities. And then just for completion, we'll write out this last step. But honestly, you probably already know that it's going to end up being 1. So that means that the GCD of 162 and 31 is equal to 1, and that means that these numbers are relatively prime. So this Euclidean algorithm is incredibly useful. It can prove the GCD or discover the GCD for any pair of integers. I recommend practicing it because it's sometimes can be a little bit tricky to remember, like which number to carry forward, which number to add on. But I think once you get this process down, it becomes a lot simpler and easier to understand going forward. Okay, so up next, we're going to go into the next section of the video. And this section is going to be the section where we have a more involved proof, but this proof is going to be absolutely crucial throughout number theory. I think I used it almost every single time I saw a GCD in number theory. So we'll switch the screen again. I think I'm going to remember all of them now. Okay. So next we're going to just go through a few major theorems about greatest common divisors. So this first theorem is going to be a combination of theorems 1.38 and 1.39. And you'll see why. It's basically because it's a biconditional, and each direction of the biconditional is considered a separate theorem in this book. But we'll explain what it is basically here. So let A and B be integers. Then A and B are relatively prime if and only if there exist integers x and y such that ax plus by equals 1. Okay, so what we're going to do in this theorem to prove it, we're going to start by assuming a and b are relatively prime and show that that means that there exist integers x and y such that ax plus by is 1. And then we're going to prove the other direction, that if there exist these integers x and y that cause ax plus by to equal 1, then we know that a and b are relatively prime. So let's go through our proof. So the first direction is this way, and this is theorem 1.38 in the book. And here we're just going to let a and b be integers where a and b are relatively prime. And this is just equivalent to writing out that they're relatively prime. It's just a much quicker way of doing so. So next we're going to define a set. And this set we're going to use the well-ordering axiom on, and then using that well-ordering axiom, we're going to show that we can find these integers x and y where they're equal to 1. So we're going to let this set equal am plus bn, where m and n are integers, and this sum is greater than 0. Okay, so since S is a set of natural numbers, or we'll note that S is a set of natural numbers. And S is not empty, since a squared plus b squared would be a member of set S. Because all we need to show is that there's some integers we could substitute in here that makes it positive, and that's true if you substitute in a and b. You square both numbers, they're positive, and then you add them together, stay positive. So by well-ordering axiom, S contains some smallest element C. And since C is in S, C is greater than 0, and C equals AK plus BL for some KL integers. Okay, so we have that shown for some K and L that are integers. Now, by the division algorithm, A equals CQ plus R for some Q, R that are integers, where 0 less than or equal to R is less than C. And this means R equals CQ minus A, which equals AK plus BL Q minus A, which ultimately, if we distribute all this out and then undistribute stuff, refactor stuff out, we'll get AKQ minus 1 plus BLQ. So all you'd have to do is distribute that Q out. You're going to be left with AKQ plus BLQ minus A, and then take that A, factor it out of that AKQ minus A, so you're left with KQ minus 1, and then you have BLQ, so factor out that B, and you're left with B times LQ. So now let's look at this value of R, and we're going to suppose, for sake of contradiction, that R equals 0, or R does not equal 0. So 0 is less than R is less than C. All we're doing is getting rid of that possibility that R is equal to 0. And this means, so since R is greater than 0, and R equals A KQ minus 1 plus B LQ, R is in that set S, right there. And since C is the smallest element, C is less than or equal to R. but we know that R is less than C. So we have a contradiction. Thus, R needs to be 0, because otherwise it would be part of that set S, and it would be the smallest element. But C is the smallest element by that well-ordering axiom. So because of that, we know that R equals 0. So A equals CQ, implying C divides A. Now, look at what we did here. So what we did here, we split out by the division algorithm, A being CQ plus R, and then we discovered certain things about R using this factorization, figured out that R is 0, and then that shows that C divides A. Now, if we use a symmetric argument, but the only difference is that we substitute B in for A, we would go through basically the same proof technique, and that would show us that C divides B. The only difference would be that you have a B here, and then this -1 would be in the second term instead, which doesn't really change the fact that R would need to be 0 in order to ensure that C is still the smallest element. So this is a perfect case where we can use a symmetric argument. Or we don't even need to say so here. We'll just state that a symmetric gives us C divides B. Okay. So B is a common divisor of, or C is a common divisor of A and B. So what does this mean? Thus, since C is a common divisor, C is less than or equal to the GCD of A and B, which equals 1, because A and B are relatively prime, which was our basic assumption going into this. So since C is greater than 0, C equals 1. So 1 equals AK plus BL, which is what we were trying to prove originally. We found the two integers that we can substitute in to make it so that it's possible to write 1 as AX plus BY. K and L are those integers X and Y. So that proves that first direction. Now let's prove the other direction. And the other direction's a bit quicker, so I should have room here, unless I decide for whatever reason to write extremely big. So for theorem 1.39, we're going to let A, B be integers such that AX plus AY, plus BY equals 1 for some X, Y that are integers. And then we're going to let C be an integer where C equals AB. Okay, so all that I'm doing here is just writing the greatest common divisor of A and B as C. It's just for notation purposes. It's just gonna be so that we can write this out a little bit quicker. Hence, C divides A and C divides B. So Cm equals A and Cn equals B for some mn that are integers. Okay? Thus, 1 equals ax plus by, which equals cmx plus cy, or sorry, plus cny, which equals cmx plus ny. So we have that 1 can be written as the product of c and some integer. So that means that c divides 1. Therefore, c is less than or equal to 1. Since 1 is a common divisor for all pairs of integers, c is greater than or equal to 1. Hence, 1 is less than or equal to c is less than or equal to 1. I feel like this is the most clear way of drawing out this, what exactly this means. So what integer is less than or equal to 1 and greater than or equal to 1? There's only one integer like that, and that integer is 1. So c equals 1. And that proves our that second conditional, and then because it proves both directions, the biconditional, it proves the overall theorem. And the reason this proves it, because remember, we defined C as the GCD of A and B up there. So what we have now is a proof of this huge biconditional theorem. And this theorem is going to be crucial in our future proofs. But one thing to note is that we can actually extend this first part of the theorem, this first direction of the biconditional, where we're saying that if A and B are relatively prime or their GCD is 1, then there exists these integers x and y such that ax plus by is 1. We can actually extend this to refer to the GCD in general. So what that means is if A and B are just integers, then there are integers x and y so that ax plus by equals their GCD. So we've only proven the case for 1 so far. So let's prove this theorem for all cases. Let's prove a general statement here. And this is very common in all throughout math. We prove some special case first, and then we realize that this special case can be generalized. So now I don't think that the other direction cannot necessarily be generalized. Well, let me think if that's true. I don't think the other direction can be, because what would that mean? That would mean that if you can write it as that, then that means that the GCD is equal to that. No, that definitely can't be generalized, because you could probably write anything is like equal to 2 or something like that, and that doesn't mean that the GCD is equal to 2. So what we're going to prove next is theorem 1.40. And this theorem is that for any integers a and b not both 0, there are integers x and y such that ax plus b y equals the GCD of a and b. Okay, so this proof is going to be very similar, so I'm going to speed through a lot of these steps because they're just going to be very, very similar looking to the previous proof. So we're going to start by letting a and b be integers such that a, b not both 0. A lot of these steps are going to be the same. I'll speed through them. And then at the end, we'll focus on the last few steps because that's where the difference of the proof is. So we're going to define that same set that we defined before. And by the well-ordering axiom, S contains smallest element C. Since C is in S, C is greater than 0, and C equals AK plus BL for some K and L integers. So by the division algorithm, A equals CQ plus R where 0 is less than or equal to R, I messed up, is less than C. Sorry, I hope you can read my handwriting. I'm just filling stuff in to make sure that it looks right at least. So R equals CQ minus A, which equals AK plus BL Q minus A, which equals A KQ minus 1 plus B LQ. If R does not equal 0, R is S and R is an S and R is less than C, but C is smallest element. So R equals 0, which implies C divides A. Symmetric argument shows C divides B. So C is a common divisor. Of A and B. Okay, so this is basically everything we did from before. This is all the proofs that we did from before, and then in that previous proof we just showed that C must be equal to 1. But now what we're going to do is show that C must be, so we've shown it's a common divisor, now we have to show that C is the greatest common divisor. And since C is written as AK plus BL, this would mean that you can write the GCD of A and B as AK plus L because C would be that greatest common divisor. So we're going to go ahead and show that if there is some divisor of A and B, it has to be less than or equal to C. So or actually we're going to show that C is equal to that greatest common divisor. So we're going to let T be an integer where T equals GCD A, B. So C is less than or equal to T. Because C is a common divisor, it has to be less than or equal to the greatest common divisor. So A equals TG and B equals TH for some G and H that are integers. Okay, so that's the first step. Hence, C equals AK plus BL, which equals TGK plus THL. And this it means that T, oh my gosh, T times GK plus HL. So T divides C. Therefore, T is less than or equal to C. Okay, so with this, since we know C is less than or equal to T and T is less than or equal to C, it follows that C equals T equals GCD. Of A and B. Consequently, GCD of A and B equals AK plus BL. And that is the proof. So that shows that for any integers a and b not both 0, there's integers x and y so that you can show that ax plus by is GCD of a and b. And what this gives us is a useful way to write out the GCD. If we're given, if we want to discover something about the GCD of a and b, what we can do is write that GCD out as ax plus by, and then we can do algebraic operations and prove things about the GCD. And let's see how incredibly useful this is with a few more quicker theorems. And honestly, we are running very long, so I'm glad that I split this up into 2 videos. This is like halfway through this section of chapter 1. And we're already at almost an hour, 10 minutes. But all good. We're going to get through these last few pretty quickly. So we're going to let A, B, and C be integers if A divides BC and A, B equals 1, then A divides C. So this is a simpler proof. Let's go through this proof quick. We're going to let A, B, C all be integers where A divides BC and A, B equals 1. So by the definition of divisibility, BC equals AD for some D integer. Thus, C equals C times 1 equals C ax plus by equals a cx plus bcy equals a cx plus a dy, because we can sub in that bc as ad, which equals a cx plus dy. Hence, A divides C. So you can see already how useful this theorem is. Oh, I didn't write out that line. Sorry. By theorem 1.40, ax plus by equals 1 for some x, y. Okay, so what you see here, this one, once you have that two numbers are relatively prime, you have a way to write out 1 as those two numbers, as like a linear combination of those two numbers, as an algebraic expression of those two numbers. So what you can do, you can actually write out a number as that number times this expression involving a and b, and then this can give you very useful results once you start substituting things in, and then you can discover that a must divide c in this particular example. Let's see another example of this, very similar looking proof next. So this is theorem 1.42. Let a, b, n all be integers. If a divides n, b divides n, and a, b equals 1, then a, b divides n. And also these give us very like fundamental truths about the GCD, and these sort of theorems, these can be used all throughout your number theory journey. They're going to be very helpful for whatever you want to end up proving. They give us basic operations of GCD that you can use all throughout. So the proof of this, we're going to let a, b, n all be integers, where a, n, b, n, and a, b equals 1. Thus, n equals ax and n equals by for some integers x and y. By theorem 1.40, 1 is au plus bv for some u, v integers. Hence, n equals n times 1, which equals n au plus bv, which equals n au plus n bv. And then we can substitute in those opposite n expressions. So this will give us byau plus axbv is equal to n, which gives us ab yu plus xv. So we have that. So we have n is ab times some integer. So n, or sorry, so ab divides n. See, look at how simple these proofs are, and now imagine if you had to go through defining that set S and then using the well-ordering axiom and then doing all this, like, all these crazy GCD properties just to get to this expression. Crazy. This saves so much time, makes things so much simpler. But yeah, let's do one more theorem just because these three theorems are pretty helpful throughout number theory. So this is saying if A and N are relatively prime and B and N are relatively prime, then the product of A and B and N is also relatively prime. So the proof here, we're going to let A, B, and N all be integers, where A and N are relatively prime, and B and N are also relatively prime. By theorem 1.4, see, these proofs are easy because you know that you're going to be using theorem 1.4. In the future, you're going to have to remember that on your own and figure out the right time to use it. But these proofs are easy because they said these are, in the textbook it says, these are theorems that you will use theorem 1.4 to prove. So 1 equals AU plus NV for some UV and 1 equals BX plus NY for some okay, so those are those. And then we're just going to write out this long expression. Well, you'll see. So hence 1 equals 1 times 1. Duh. Well, what does this mean? We can substitute each of these in. So we have AU plus NV. And figuring this stuff out, it's just going to take a lot of practice with proofs. Yeah, it just takes a lot of time, and you just have to try a lot of things, and something eventually works. That's kind of the art of proof. It's a lot of just coming up with some creative way of writing things out and reorganizing things just to make things work. And you start to figure that out after a long time, spending a lot of time with proof. Things like this are harder for me to figure out now, but it's cool to like start getting back into proof because a lot of that muscle memory just comes back. Like before I record all of these videos, I go through and like try to figure out each of these proofs, and I feel like I'm learning a lot and remembering a lot of stuff from college, which is really nice. And I really enjoy proof, so this is really fun for me, just writing these videos and writing stuff out. So but it just takes a lot of practice. If you enjoy it, you'll put in the time, you'll put in the practice. But so we'll write this out. And this is just the distributive property. FOIL it out, and yeah, you'll be able to write these 4 terms. So 1 equals, so what do we have here? We have AB times UX. And then we can also factor out an N from all the rest of these terms. So what do we have here? We have 1 written out in terms of AB times an integer plus N times an integer. Now, what does this mean? Well, if you remember from that theorem that we proved originally, just about in the case of 1, the biconditional holds in the case of 1. So if you can write out 1 as the sum of an integer times an integer plus an integer times an integer, then those two integers are relatively prime, because that they add up to 1. So by theorem 1.39, the GCD of A, B, and N equals 1. Okay, so that is everything that I have for this particular video. Let's zoom out. We did a lot today. Oh, and we are zoomed very far out. So this is all that we have done for today. And that is also all that I have for today. So I'm going to open it up to the comment section. Please let me know if you have any questions. This was a long video. An hour, 20 minutes is a lot of time to spend on a math video. So I hope you enjoyed it. I hope you've stuck with it and learned a lot, and hope you enjoyed. And yeah, let me know if you have any questions. I have my Discord below if you have anything to ask, if you're curious about anything. And actually, let me just put up this so that you can look at the full thing a little bit more. And if you like the video, please like. If you want to keep following this series, if you've enjoyed the series and want to be notified every time a new video comes out, which at this point will be like once or twice a month, tends to be the way I do it. And yeah, if you want to get those notifications, please subscribe, hit the notification bell. If you really want to support, if you really enjoy the content, I have a Patreon link below as well that you can go support on. And yeah, and then I also have my Discord. Feel free to ask questions. I talk about all of my videos in that Discord. And I get a question or two maybe every month. Not super common, but yeah, I try to respond within like a week or two. I'm not always on Discord or always have time to respond. But if it's a simple question, I'll try to get to it quickly. I need to get better about that. So yeah, feel free to join the Discord. It's also hard for me to know when people ask questions because the Discord's pretty dead right now. But also, if you have questions, there's the comment section below. I'll try to get to your comments whenever I can. And yeah, I think that's everything that I have for today. So thank you all for watching, and I hope to see you all in the next video. Peace.